Hello everyone and welcome to my very first lecture. I believe Tim already introduced me in the first lecture. My name is Luis Hermann. I'm currently doing my master thesis at Tim's lab and I'm helping Tim with the preparation of the lectures, and I'll be doing some of the lectures of the semester myself. So today we're going to talk about ensemble methods, and we're going to cover several subtopics, namely decision trees, random forests, and bagging. So in the last couple of lectures, you've already learned about a number of different predictors for classification and regression tasks. And in many cases, those predictors are going to work just fine by themselves. But in other cases, those classifiers are not going to be sufficient to do regression or classification tasks. And when that is the case, we call these classifiers weak classifiers. So consider this example where as input you get an image of a car or an image of another object, and you're supposed to tell whether the image is of a car or not. Now we could have a weak classifier that looks for tires in the image, and if so, it tells you that it's a car. And we might have another classifier that looks for headlights in the image and tells you that it is a car. And I think it's pretty obvious that each of these classifiers by themselves are not particularly good at predicting whether an object is a car. Why not? Well, for starters, your weak classifiers are going to miss out on a lot of samples. So for instance, if you think of this example where we have an image of a car from a top-down perspective, our weak classifier checking for tires is not going to be able to find any tires in this image, and so it's going to tell you that the car is not a car. And likewise, the other weak classifier checking for headlights is not able to detect any headlights in this image, so it's also going to tell you that the image is that the object on the image is not a car, even though it clearly is. And the other problem that you may encounter is ending up with a lot of false positives. So for instance, if you think of this example where we see a bicycle on the image and we apply the weak classifier checking for tires, it's going to encounter tires on the bicycle. So it's going to conclude that the object depicted has to be a car. Likewise, if you apply the weak classifier checking for headlights, it's also going to find headlights in the image. So it's going to conclude that the object has to be a car, even though it is not. And I think this example shows very nicely that if you use just one classifier, possibly a weak classifier, and even multiple of those weak classifiers, you might not necessarily end up with good predictions. But I think it's also intuitive to see that if you start combining more and more of those weak classifiers that check for other features, you might actually end up with something that can be used to build a good predictor. So for example, you might also add a classifier that checks whether the object has a windscreen, and another another classifier which checks whether your object has back seats. If you start adding up more of those features and check if the majority vote is positive for a car, then there's a good chance that this vote might reflect the reality of the sample that you're trying to classify. So let me give you a bit more of an intuition why combining several predictors into a better predictor might work. Now for this example, I'm going to look at a very large population of people, so not models, but people. And this population consists of laymen making up, 80% of the population, and experts making up 20% of the population. And now the task at hand is to answer a yes or no question, for example, for a quiz. And we need to come up with the right answer. And how do we proceed? Well, what we do is we sample a committee of n people from that large population, and then we submit the answer of that committee to a majority vote. So here in this example, we sampled 3 people from that large group, and the resulting committee provided 3 answers, so yes, yes, no, and the majority vote in this case would be yes. And now we can look at how these committees are going to perform for different sample sizes. And the way we are setting this up is we're assuming that the probability of a layman being right is just 50%. So they're essentially just doing a random guess. And the probability of our expert being right is going to be a value that's larger than 50%. And we can tune up the probability of the experts being right and observe how the probability of getting a correct majority vote from the committee changes. And what we observe is that for a single individual, if we just pick a single individual from our population, then the probability of getting a correct majority vote is going to increase very slowly with the expert correctness probability. But if we increase the number of individuals in our committee, the probability of getting correct majority vote is still going to increase slowly, but it's going to be at all times greater than the probability of getting a correct majority vote for a single individual. And in fact, if we tune the number of individuals for our committee up even further, the probability of getting a correct majority vote becomes better and better. So for instance, if we take 200 individuals, you can see that at an 80% probability of our expert being right, we already have an almost 100% probability of ending up with a correct majority vote. And now mapping this back to our models and to our weak classifiers that we want to combine to better predictors, the idea is that even if we have some weak classifiers, if we, by dumb luck, we end up with some good classifiers and we combine our set of classifiers, we can end up with a very good majority vote. So we can end up with a very good predictor. And basically, there's two different methods of how you can combine these predictors into better predictors, which are called bagging and boosting. Now, in this lecture, we're only going to look at bagging. Boosting is going to be covered in the next lecture, and we're going to look at bagging through the example of random forests. So we need to be able to grow a single tree before we can grow an entire forest. And so before we deal with random forest, we're going to first talk a bit about decision trees. And here on the left, I've already set up a small example for a decision tree, which works as a predictor for the question whether you should watch this video. So let's see. If you're new to bagging, then yes, please do watch the video. If no, I'll delegate you to the next question. Have you already heard about decision trees? If the answer is no, do watch the video. If the answer is yes, are you confident that you're going to score 100% in your next exam? So if the answer is yes, well, whatever, don't watch the video, you don't have to. But if no, please do watch the video. Now, what you may notice as we move down through the decision tree is that we have two types of nodes, as in any tree. We have inner nodes, which represent a decision, and this decision is made by testing a condition. For example, are you new to bagging? If the answer is yes, we move down the left branch, and if the answer is no, we move down the right branch. The other types of nodes are leaf nodes, which represent a prediction. So in this case, we have the prediction watch or don't watch. So two types of labels or classes. And I'm afraid in this case, in most cases, you're mostly going to end up finding that you have to watch the video. Now, in machine learning, we're typically dealing with two different kinds of labels for our data, namely with continuous labels for predicting continuous variables, and with discrete labels for dealing with discrete variables. And there's actually two different types of decision trees, namely regression trees. So we talk about regression trees when we're doing a regression task, and we talk about classification trees when we are doing when we're doing a classification task. So since we also started with linear regression rather than logistic regression, let us also here start with regression trees before we move on to classification trees. So what really any decision tree does, so both regression trees and classification trees, is they structure the input space into different regions. So in this case, into regions R1, R2, R3 through R6. And so the inner nodes of our regression tree are associated to a splitting variable xj into a splitting point c. So what does this mean exactly, this splitting variable xj? Well, remember that our input data in machine learning typically has a high number of dimensions, with each dimension representing a different feature of the data objects. And what we want to do now is we want to conduct a split along a single of those dimensions. So we want to look at a single of those input features. And we have a splitting point C, which segments our space along that dimension into two half spaces. So given splitting point C and a splitting variable xj, the first half of the space is going to be all points x for which the jth dimension is smaller or equal, or so the value of the jth dimension is smaller or equal to c, and the other half of the space is going to be all points for which the jth dimension is larger than c. Now, so yes, again here, this particular node in our example splits our space into two half spaces. Here, where the second coordinate is smaller or equal to 2, and the second half being all points where the second coordinate or the value of the second coordinate is greater than 2. And so if we look at what this looks like in our space, we get a split like this. So this half of the space is going to be everything down here, and our second half of the space is going to be everything up here. Now, moving on to the next region, or to the next node, in this case, further down the tree, this node now conducts a further split of our space into two further subspace, into two further half spaces, S1 of 1 and x1. So all points for, so here in this region, all points for which the first coordinate is smaller or equal than 1. And here, the second half of the space, all points for which the first coordinate is greater than 1. And now, what about the leaf nodes? Well, the leaf nodes M are associated to a region M and to a constant prediction C of M in Rm. So, for example, this orange highlighted node over here covers a region R1, and it generates a prediction of Cm equals to C1 with value 1. Now, what exactly does this mean for our full predictor? So for our full predictor, this means the following. Let us assume that we feed data point x into our regression tree. So if that point x lies in a region Rm of the input space, then the output of our full model predictor is going to be Cm. So it's going to be the value of the respective node for this region in the regression tree. So if you read Hastings and Tibshirani, you might also find this closed expression for the full model predictor, but this is just a fancy way of writing this down in case you are interested. Now, let us look at an example from top to bottom of the tree. So let us assume we have an input x equals to 0.5, 0.5. So I'm not sure if you can read this done here, but this point would lie in region R1 of our input space. And so the prediction of our model is going to be f of x equals to c1, so the output value for region R1, which happens to be 1. And we can see this by just following the decision path down to the leaves of the regression tree. So obviously x2 is 0.5, which is smaller or equal than 2. So we move down the left path of a regression tree. Then we check the next condition. So x1 is 0.5, which is smaller or equal to 1. So again, we move down the left path of the tree, and finally we end up with a leaf node which tells us, okay, the output for this particular input is 1. So now we know how we use a regression tree, so to speak, so how we classify with a regression tree. But what we don't know yet is how we compute that regression tree in the first place. And so a good starting point in machine learning when you want to build some classifier is always to think about what your loss function is. And for regression trees, the loss function that we're going to use is MSE, so mean squared error, which is what we typically use in regression problems. And now we define a so-called impurity score, or a loss for each individual leaf node of our tree as follows. So basically we look at all points from our training data which lie within a certain region Rm for this leaf node M, and then we subtract, so then we look at the squared deviations of our of the prediction of this leaf node from the actual values of the training data or of the training points within that region. And well, we sum everything up and take the mean as usual. Yeah, here's M is just the number of points xi from the training data that lie within the region Rm. And then for the total loss, we simply sum over the individual losses or impurity scores of all leaf nodes in our tree to get the entire loss. Now, how do we use this loss to start growing a regression tree? I mean, let us assume that we have no node yet, or even better, let us assume that we have one single output node, and so one single leaf node for our regression tree. Now, what we do for growing our tree is we want to split this leaf node into two further leaf nodes. And so the way to split this leaf node is, of course, is to get a new inner node with a split variable xj and a split value c, and two leaf nodes that are beneath this inner node. And so the half space S1 for this variable is going to be assigned a new value C1, and the half space S2, which searches from subdividing the space at this leaf node, is going to predict a value C2. And now the optimization objective when we do the split is we want to find good values. We want to find a good splitting variable, and we want to find a good value C for that splitting variable. And not only that, but we also want to find good values for our prediction at the leaf node. So we want to find good prediction values C1 and C2 for those new leaf nodes. So we end up with an optimization expression which looks a bit complicated. So we want to minimize the loss of this node C1, so Q over C1, and plus the loss of C2, so Q over C2, and we want to minimize that over our splitting variable J, our splitting point C, and our prediction values C1 and C2. Now, luckily, this minimization can be simplified a lot because, well, we're using mean squared error for our impurity scores. And when you have mean squared error, obviously or not obviously, but so the value that is going to give you the minimum for a mean squared error is quite simply the mean of all the values that you get. So if you have a number of training data points xi that lie within this region as 1, the value C1 that is going to give you the minimal mean squared error is actually the mean of all predictions yi. And likewise for C2, the best prediction is going to be the mean of all values yi for all the training data that fall within the region S2. And this leaves us with a minimization that's much nicer to behold, because now we're only minimizing over our split variable xj and our split value z. And so C1 and C2 now depend implicitly on J and C. So how can we minimize this? Now, the most straightforward way is to just try out all possible variables xj and splits c. I know this sounds horrifying, but it's actually not as bad as you think, because, well, let us assume that we have n data points and we have selected, let us look at a specific variable xj. So we can sort our data points along this axis xj, and then we can just look at splits for any 2 subsequent points along that axis. So if we have n data points, we only have to try out n-1 possible splits. And then we repeat this for all possible x's. So if our data has d dimensions, we repeat this for d dimensions. So in total, we would have to do the step d times n-1 times. So we would have to calculate d times n-1 losses, and then we would simply pick the best loss that we end up with, or we would pick the best. We would pick the best split variable and value for that loss. So you may be thinking now, wait a minute, why do we only have one possible value for our splits? I mean, I can just shift the split around. I mean, this is a continuous space, so I can choose C however I like. Why do I only have to pick one value? And well, you're right. So there's an uncountable number of possible values for C that you could pick, but this is only relevant with respect to our testing data. With respect to our training data, we can just pick any value for Ci between xi and xi plus 1. So we can pick any value here that we like. But it's a reasonable assumption that if we take the mean between these 2 points and our training data is representative, then this split is going to generalize well on our testing data. And now you may be thinking, wait a minute, what if our data is discrete? Well, in that case, it doesn't really make sense to take the mean between the subsequent values. So in that case, rather than taking the mean, we'd just take the current value of the sequence. So for example, if we're looking at these points, then we would choose Ci xi for our separator value C. So I hope this becomes clearer with a little example. So let us assume we have a data set with 2 dimensions, which looks like this. And now the first step is we select a candidate variable x1 for our split. And we sort x and y as in ascending order for that candidate variable and end up with something like this. So as you can see, values along x1 are sorted. Then we select a candidate for our split point C. So the first candidate here in this case would obviously be the value between 1.2 and 1.0, sorry, and 2.0, so 1.5. And this split value C creates split S1 and S2 as follows. So it creates this split, or it creates a split which covers these nodes and these nodes. And now we calculate the means for those respective splits. So inside this region, we only have one of our training data points. So the mean of the split here is just 3.0. And over here, well, we have 3 data points and the mean of these data points is 4.5. So we calculate the total impurity score for our respective C1 and C2, and we end up with a total impurity score, or a total loss for that split of 6.5. So then we select our next split point C. In this case, so between this and this point, so 2.5, and this split value creates new splits S1 and S2. So again, these points of training data are in region S1, these points of the training data are in region S2, and when we calculate the means of those splits, we get 4 and 4.25, and this gives us the following loss or impurity score. And what we just did, we repeat for all possible split variables xj and split point c. And when we do that, we end up with a table which gives us the prediction constants C1 and C2 and Q total, so the losses for all those possible splits. And now that we have this table, we can simply select the variables the variable xj and the split point c for which the loss Q total is smallest. And in this case, that's x2 and the split value 6.0. And for Q total, we end up with a loss of 3.5. So now that we have that, we already have the first prototype of our tree. So we have the first inner node where we have a decision or a condition testing whether x2 is smaller or equal to 6.0, and then we have a left branch leading down to a leaf node with value C1 3.5 and a right branch leading down to a leaf node with prediction constant 6.0. So obviously a tree with just two nodes, two leaf nodes, is not going to be particularly good. So what we need to do now is we need to recursively repeat this procedure on our leaf nodes. So we could, for example, go look at the left leaf node here, and then we would repeat the same splitting procedure again, end up with new leaf nodes, and apply the splitting procedure to them as well. So something that is nice to point out here is that at any leaf node M, we only need to consider that part of the training data which enters that region, right? I mean, if we cascade down our training data through the leaf, through the tree, part of the data is going to end up here in this half space, and the other part of the data is going to end up in this half space. So at each node, we're only going to have to consider that part of the training data which actually is in that half space. Okay, so let's just look add one more example to make sure you know how to do this if you were on your own. So let's assume we want to continue splitting the tree, and let's say we had selected this node to perform our next split. So what do? The first thing is we reduce our data set to x intersected with S1 of 6.0 and x2. So we select all points from our data set which lie in the region of this node. So in this case, it's really simple because those are simply all the points for which x2 is smaller or equal to 6.0. So we take our original data set over here and we select all the data points for which x2 is smaller or equal 6.0. So, okay, this data set goes in, this data point goes in, this data point doesn't go in because x2 is 7.0, which is larger than 6.0, and this data point goes in. Okay, so we end up with this new data set. And now we do the exact same thing that we did earlier. So we continue with our reduced data set, and now we select a candidate variable for performing our split. So let's start with, say, x1. And now we sort our x epsilon in ascending order for our candidate variable. So in this case, since we have selected x1, we'd end up with a sorted data set that looks like this, sorted for x1. And then we do the other steps that we did previously for the first node, and that's pretty much it. So I hope from this example, it's now clear to you how you would have to proceed in this case. So when do we stop this procedure? Well, there's different ways of doing this, but so an important insight is that every time we perform a split on our tree, the training data that passes through to a new leaf node is going to thin out even further. So at some point, we're going to be left with leaf nodes where we only have a small number of training data. So what we could say is we set a threshold t, and as soon as the number of points from the training data that are assigned to that region is smaller than this threshold t, we stop splitting at that leaf node, and then we check that condition for each leaf node of the tree. So obviously the minimal threshold that we could set is 1. So if we only have one training data point remaining at a leaf node, it doesn't make any sense to keep splitting that node. So this is the maximum number of leaf nodes that we could end up with for our tree. But even though we could do this, and it's going to minimize the loss of the tree, it's certainly going to overfit our data. So this is not a criterion you should consider under normal conditions. So something which might make more sense is to look at how much the loss decreases when we perform a split. So what we could do is do something like the elbow criterion. So we could look at how much the loss decreases when we perform a split at a node. And if the decrease of loss is below a threshold theta, then we do not perform that split. The problem with this greedy approach is that so at a certain level of the tree, we might have a bad split with hardly any decrease of loss, but then on a lower level, on that branch of the tree, we might end up with a better split that increases our loss greatly. So so you should be wary about taking this greedy approach. So again, here an example to visualize the problem. So for this example, I just fitted classification trees on the scikit-learn California housing dataset, and I just tried out different maximum numbers of nodes for the trees. And as you can see, the mean squared error for these trees decreases exponentially with the tree size t. So this is a good property, but again, we need to decide which tree size is reasonable to choose for our model. So one thing we could do is we could we could do cross-validation or just normal validation and look where the validation loss starts becoming worse when we increase our size t. But there's actually a better approach that we can take, and that approach is pruning a tree. So the idea is that first we grow a tree to the full size, and then we start cutting out connections of that tree and reducing the size to end up with a good tree. And this method is called cost complexity pruning. So again, the idea is we keep populating our tree with leaf nodes or splitting until the number of training data points for each leaf node is just 1. So we've reached the maximum size of our tree, and then we start removing leaf nodes and see how the loss changes. Now, if we don't modify our loss function, we're just going to find that the loss increases. That the loss increases again. So in order for this to actually make sense, we need to modify our loss function. And the modification that we introduce is that we add a penalty for our tree size. So we introduce a regularization term which penalizes the size of a tree. So this t might be either the total number of nodes in the tree or just of the leaf nodes. And if we start removing leaf nodes now, we might encounter situations where the loss decreases if we remove a leaf node. And this is precisely what we want to have if we want to reduce the size of the tree. And then we would just try out all the possible combinations or a given number of combinations and pick whatever tree gives us the minimal loss. Now, the only problem with this is, of course, that we introduce a new hyperparameter alpha, which must be based on experience values. But at least conceptually, this is a quite nice way of doing it. So now we're finally through with our regression trees. And as promised, classification trees are going to be very easy with this. So again, classification trees are almost the same as regression trees. So again, we have a splitting variable xj and a splitting value c. Now, the first change that we introduce is that since our classification tree works with discrete labels, our constants c1 and c2, so our prediction values need to be from a discrete space. And since they need to be from a discrete space, the way we choose these values, C1 and C2, when we perform a split, also needs to be changed. So previously with regression trees, we calculated the mean over the respective data points. And now what we do is we take the top vote at that split. So this is just a fancy expression, but what we're doing here is just we're counting the number of training data that has a certain target value or a certain label, and then we pick whatever label has the most occurrence. So a simple example where our splitting variable is x1 and 2 for this data set. So obviously 1.5, 2.0, and 0.5 are going to be moved down this half space. So yeah, since the labels are 0, 1, and 0, the top vote of the labels is 0. And on the right half space, we only have one data point, well, the output label is 1, so the top vote is going to be 1. However, now we have a problem because we're using discrete valued constant Cm, and we have discrete valued predictor. But we're still using mean squared error loss, which is not really suitable for classification problems. So we need to deal with this. And how do we do this? So one possible answer is, first of all, let us look at the proportion of predictions k at a leaf node m. So we denote this as p m of k, and well, this is just going to be the number of training data points which get assigned to region R of m, and for which the label yi equals k, divided by all training data points within the region Rm. So basically, if we just started feeding data points from here, we would look at all data points which get fed down here, for example. That would be all points here, and then we would look at the number of points for which we get a particular label. So let's look at a specific example. So for instance here, M is our first node, so it's our first leaf node, which is this one. And so we look at the label 0, which in this case is the proportion of correct predictions at this leaf node. And well, as we already saw earlier, we have these points 1.5, 2.0, and 0.5, which get assigned to this left branch of the tree with labels 0, 1, and 0. And well, only 2 of these labels match the label 0 that we're looking at. So yeah, we end up with a proportion of correct predictions at leaf node m of 2/3. And then we can use this proportion PMK to define a couple of different loss functions. So the most simple loss function that we can think of is a misclassification error. So here PMCM, remember CM is the predicted label for a node M. And so this PMCM, this is the proportion of training data points that get the label CM, so which get correct prediction. So logically 1 minus PMCM is going to give us the proportion of incorrect predictions. And well, since here we're just inserting the definition for our label CM, namely we take that label CM which gets the majority vote. So if we have a majority vote, a majority number of training data points giving us this label CM, logically also we have a majority proportion of training data points giving us this label. So then we also have the Gini index. Here we have an expression where we sum over a PMK prime, so for different K and K prime. And we can also rewrite this as this expression. And well, cross entropy you already know. And now these loss functions do not look like they have a lot in common. But let us look at these loss functions for the binary classification problem. So here again, the misclassification error looks pretty much the same. The Gini index we can reduce to a nicer expression because we only have 2 labels, 0 or 1, and no matter which label k we pick, since the expression is symmetric, we can reduce this to this form. And for binary cross entropy, now we have the same issue as for the Gini index. So what we notice is that for all these loss functions, as we increase PMK, well, our loss initially increases, then we hit the maximum of 0.5, and then our loss starts decreasing again. So we have a symmetry around 0.5. And well, actually this is quite logical when you think about it, because well, let us look at an example to understand this, and let us do this for the misclassification error, because it's the simplest way to see this, and for the other losses it's pretty much the same. So let us assume that from our training data, let us assume that 100% of the training data has a label 0 and 0% of the training data has a label 1. So then the proportion PM0, so PM for label 0 at this node M, is going to be 1. The proportion PM1 is going to be 0 because, well, 0%. And so since 100% of the training data has the label 0, the majority vote is going to be 0, and thus our node M is going to get the prediction constant CM0. And since all of our training data has the right label 0, the loss for the misclassification error is also going to be 0. So this is where we start off here. Now let us slightly decrease the number of data points which have label 0. So now it's only 90%, and 10% of the training data points have a label 1. So now the ratios PM0 and PM1 are 0.9, 0.1, and well, so 90% is still a majority of the training data points. So our label CM, or so our prediction constant CM still stays 0, but now we have 10% of the training data points which get get assigned the wrong value. So we have a misclassification error of 0.1. And well, now we can see that the loss starts increasing. So as we increase the number of training data points that have a label 1, the loss starts increasing until it reaches the maximum of 0.5. And what happens then? So for example, so once we cross this point, so in this case, our the proportion of training data points that have label 0 has reduced to 40%, while those with label 1 has increased to 60%. So now our ratio is 0.4, 0.6. Now what happens is that the majority vote at this node is going to flip, because, well, previously the majority vote was for 0, now the majority vote is for 1. So our prediction constant CM changes from 0 to 1. And now the fact that we have 60% of our training data giving us with a label 1 is no longer an issue, because now this is what we want to have. And so now the problem is our training points which have a label 0, because those make up 40%, and they have the wrong label now. So once we pass beyond this point, our loss is going to again start decreasing. Now let us look at some properties of decision trees. So what we've already seen is that decision trees are very nice to interpret because we have split variables that correspond to features in our data, and we have split values that correspond to decision boundaries. And well, we can just follow down a branch in our leaf and basically see how all the decisions play out and end up with prediction label. Now there's another very nice property of interpretability for decision trees, namely that we can easily get a sense of the importance of features, or so of variables of our data. And the way we can do this is by looking at the change of loss when we add new leaves nodes to our tree. So remember when we looked at how the loss evolves as we increase the number of leaves for our tree, remember that the loss decreases exponentially. So every time we add a new leaf to our node, unless we use some kind of penalty, our loss is going to decrease. And well, this decrease of loss can calculate it in this form. So we just take we just get the impurity score for the node that we had before the splitting, and then we add the impurity scores for the nodes that we get after the splitting. And well, now the idea is that well, we can interpret this change of loss as the importance of this node. And this node is associated to a specific to a specific feature or variable xj. So it's not too far-fetched to think that if we add up these losses for all nodes m that have a splitting variable xj, we're going to end up with the importance of that variable xj. And if we do that, for instance, for the breast cancer dataset from scikit-learn, you get very interesting results. So for instance, you see that there's this feature called worst perimeter. So don't ask me exactly what these values mean, but we see that there's one variable called worst perimeter, which covers most of the importance, and then the next most important feature is something called worst concave points, and from here on all other variables are much less important. So let us sum up some of the advantages for decision trees that we've already talked about. So first of all, we have high interpretability. Most importantly, high interpretability of the features. So this allows us to understand basically what the model is doing and how we are ending up with certain predictions. But it also gives us a good feeling or a better sense of the structure of the data, because basically the idea is that if a feature of the data is important to get a good model of the data, then it clearly has to, tells us something about the structure of the data and of the underlying problem. And the second advantage that we talked about is that we can use decision trees both for continuous and discrete labels, so for regression and for classification problems. And well, this is obvious because you can just use regression trees or classification trees depending on your problem. But there's also a couple of disadvantages, the most notable being that decision trees usually have a high variance. And the reason for this is basically that errors in inner nodes propagate all the way down to leaf nodes. And well, let's stop and think about this for a second. So let's assume you have a trained model, and let's say we have a new data point, a new unseen data point, which we did not use in training. Let's say the label for this data point is 3. So we feed our data point to our model, and ideally we would walk down this right branch and all the way down to this node and get the right result. But now let's say that we take a wrong turn here to the left, and well, we end up in this node maybe. And the problem is that well, so the idea is that if, for instance, there are no other leaf nodes with a 3 in this branch over here, once we take this wrong turn, it's going to be impossible to recover from this error. Now, the second disadvantage is that, well, decision trees do not have a smooth prediction surface, and this leads to higher training and test errors for regression, but it's not really a problem for classification trees. So this is just an issue of regression trees. But these two properties combined make for a worse generalization of a decision tree, and particularly of regression trees. So since we want to use the nice features of decision trees, we need to do something about the disadvantages. And well, this is where finally our ensemble methods come into play. And we're going to start with bagging as promised. So bagging stands for bootstrapping and aggregating, and those two words just refer to the two steps that we perform with this procedure, which is actually quite straightforward. So let's see how it plays out. So in the first step, bootstrapping, we're given some data x and y, and we want to create new data sets xb and yb from our original data. So how do we do this? Well, it's simple. We just draw subsamples of our original data with replacement, and then we end up with these bootstrapped data sets xb, yb, or bags, and we use these bags to train individual models fb. So each of these bags is used to train a bootstrapped model fb. So that's the bootstrapping part. Now moving on to the aggregating part, we want to combine those models fb that we have trained into a single predictor. How do we do that? So for the continuous case, we just compute the mean over all predictors. So given a data point x, we compute the output for all our bootstrap models, and then we just compute the mean over those outputs. And in the discrete case, again, given a point x, we compute the model outputs or the predictor outputs for this point x for all our bootstrapped models, and then we just take the majority vote of those models. So let us look at an example. So here I have a data set with 6 data points. It's ridiculous to do this for such a small data set, but let's just use it as an example. So our number of data points is 6. We're going to say that the number of data points per bag, m, is 4, and we're going to create 3 bags. And well, in our first step, it's going to look like this. So we're just going to randomly select x3, y3, blah, blah, blah. And we do that with replacement. So this is an important point of bagging. So we do the selection of the samples with replacement. So in this case, for example, x3 and y3 appears 2 times. So it's possible for data points to appear multiple times in our bagged data sets. And then we perform a training and end up with a tree, in this case T1, representing a function f1. Then we do the same thing for our next bag, b equal to 2, and here again we sample the same data point 2 times. Again, we train our model f2, and we do the same thing for b equals to 3, train model f3, and then we aggregate our trained models. So in the regression case, we just take the average of all those models. So let's assume we now get a new input point, x, which we want to predict. So our first model predicts f1 0.2, this one 0.8, and f3 predicts 0.5, and the average of all those predictions is 0.75. So that is our final prediction for that data point. And for classification, we just take the top vote. So in this case, our first model returns 1, second model returns 1 as well, and third model returns 0. So the top vote is 1, and that's the output that we generate for our input data. And you're onto something if you think this is a bit too easy, because even though bagging does work quite well, we have this problem that the predictors can be strongly correlated, and this is especially the case for decision trees. So remember that we sampled our bootstrapped data sets all from the same original data set. So this means that our bootstrap data sets are all going to look very similar to one another. And if our bootstrap data sets look similar to one another and we have decision trees, our decision trees are also going to look similar to one another because we're going to have similar variable split and thus are going to end up with strongly correlated trees. So this correlation is a problem because the correlation limits the variance reduction that we can get, and thus it limits how well our model can generalize. I'm not going to do an in-depth derivation here, so if you want to see this, you can go and read the section on this in the tip Shirani, but just let me give you the general idea. So the idea for seeing this is that you model your predictors as be identically distributed but not independent random variables, and then you end up with this expression for the variance of the backed model, where so here's sigma squared is the variance for each model, and we assume all models have the same variance since they're identically distributed, and we assume that the models, so each two models have the same correlation rho. And now if we let the number of models in our ensemble go against infinity, we end up with this reduced expression where we have the variance of the backed model depending on the correlation rho and the variance sigma squared. So we need to get rid of the correlation here somehow. And the way we can do this is by increasing the randomness of our decision tree generation process. Because if the process of building the trees becomes more random, our trees are not going to look that similar, even if we have similar bootstrap data sets. And so the correlation is going to decrease. And our hope is that even as we increase this correlation rho of the decision trees, the variance sigma squared is not going to increase. So we actually have an advantage from randomizing our building process. And this is where random forests come into play. So random forests are almost exactly like bagging, and the only primary difference is that we change how the trees are grown. So in a sense, it's a specialized case of bagging for tree structures. And the way we do this, so again, just like with bagging, we bootstrap our data set to get a number of bags. And so let's assume we have trained a model for one of those bags, and we're looking at an individual node M, at an individual leaf node M of that bag model. So what we do then is we select n prime variables xj at random, where our n prime is smaller than the total number of variables. So we select a subset of variables, and then we keep the best split variable on point, and we do a split. So then we split our node into two children nodes. So as you can see, this is pretty much the same way that we build decision trees in our vanilla way of building decision trees. However, instead of looking at all variables xj, we only look at a subset of the variables. So remember, in the vanilla method, we looked at all possible split variables and all possible split values. Here, we just look at a subset of split variables, which is selected randomly, and the number n prime which you select, well, again, so this is something that you have to try out, and a hyperparameter that you have to optimize, but these are recommended values that you use for regression and classification. So let us do one final example for random forests to see how this works. So let us assume that we have this data set with 4 dimensions, and with a number of 6 data points, and we want to create bags which have 4 data points. So we randomly select 4 samples from this data set, and well, conveniently, and now we perform a random selection of variables. So here our n prime is just going to be set to 2. So we select 2 variables randomly, namely x1 and x3. And well, now we optimize or minimize our loss over J and C, just as we did for normal decision trees, and end up with a table of possible values for Q total. And well, in this case, I selected x1 and or the values for x1 and x3 such that we get the minimal value for this particular split, 2.57. So our new tree node, our new tree node is going to look like this. So now let's see how random forests perform compared to bagging. And for this, I've set up a small example where I took the breast cancer dataset from scikit-learn again. And so for the base models, so for the individual predictors, I took decision trees, or actually regression trees with a maximum number of nodes of 4. So they are actually very small regression trees. And then I performed bagging and built random forests with those tree stumps, so to speak, for a different number of predictors, so for a different number of weak predictors. And I looked at the accuracy of the bagged or random forested predictors. And the first thing that you observe is that, well, you get pretty high accuracies, almost 100% in some cases. And well, I think it's fair to say that most of the time the random forests are clearly better than the bagging or than the bagged predictors. So in some cases, this is not the case, but I think there's a clear tendency for the random forests to be better than the bagged models. So that's it for today's class. Hope it wasn't too confusing. Next week, we'll be talking about the other aggregating method, which we talked about, so about boosting. And we'll do this through the example of the Viola-Jones algorithm. So we are already starting to delve a bit deeper into topics of computer vision, which will be very important for neural networks. And I'll be doing the Q&A sessions this week. So hope to see you there and have a nice day.